Statistics are one of the more complicated things when it comes to doing discovery paradigm research. And one of the reasons for that is because statistics themselves can be exceptionally complicated. And the idea is that the mathematics that go into quantitative research, can't just be pluses and minuses here, right? It's got to be something a little bit more complicated, especially we're trying to make generalizations across large-scale populations. So when it comes to statistics, what I'm going to be introducing for you here are some very basic understandings of things. And so it's not going to be really complicated. I'm not going to get into some hardcore inferential statistics, the types of data analysis techniques that are out there. Instead, I'm going to give you a basic overview of what's to come in the sort of statistical research that's out there. If you're looking for more hardcore measures and really wanted to get into the stats game, I can tell you there are more advanced classes like Com 408 that are typically taught over on the Tempe campus, or other classes in statistics, obviously over in mathematics if you're really into the stats world. So for the social scientists, this is going to be the sort of very basic understanding, but hopefully it allows you to get an understanding as to how this research can be conducted and the types of predictions that can be made based upon it. Well, when it comes to doing statistics work, the first thing that happens after any data collection measures are complete in stats, let's say you've done all your surveys, you've run them all, and now you're trying to tabulate them, is a process of data reduction. And I've been a part of this process in the work that I've done. And this is where you take the large data set, loads and loads of numbers, and then you want to reduce it into some analyzable, useful, and consequential terms. Now, part of that process includes cleaning of the data. And I've spoken about this before. That process is things like, finding out those really abnormalities that are inside the data, things that you want to take out, like the person who puts down on a survey that, when you ask how many drinks they had the last time they drank, and they put 100. That's obviously incorrect, and so that's a lie. That person would be dead. And so that's not something that's going to be fitting in the data. And so scrubbing the data means that you get rid of those surveys that are obviously incomplete, or that they were filled out with either survey fatigue or without any sort of care. So things like reverse items, where you put in an item that should be scored in one direction, and then people aren't paying attention, so they just put down, on a scale from 1 to 7, 7, 7, 7, 7, 7, 7, 7. If you throw a reverse item in there, it should go 7, 7, 1, 7, 7, 7. But if people don't catch it, then it means they're not paying attention to the survey. So you can choose to throw that survey out. But the data reduction process also includes the stripping out of unique identifiers. And so if you wanted to know whether or not one specific person answered in a particular way, well, in the stats world, that's not going to be helpful. And so you pull those things out, and instead you look at them in the aggregate form. Things like groups, groupings of age, sex, class standing, whatever it is you're looking at. Now, some helpful reminders on measures of central tendency, because I'm going to be referring to these later on, are things like mean, median, and mode. Now, you may have learned these in some other mathematics class, even as early as junior high or high school. These are actually really common terms. But they're actually really important. We just don't really talk about them all that often. But the mean is the statistical average. This is the one where if you add them all up and you divide by the number, then you get a statistical average. And so if there are 30 people in the class and you take an exam worth 50 points, I'll add up all the scores, what everyone got, and divide by 30 to get the average score. That's the mean. The median is the score that's in the dead center of the class. And so if there are 50 points, 30 people in class, I'll take usually the average between the person at the 15th and 16th level there, and there's your median. And so the median is the one that's in the center point of the data, which is a different sort of statistical average, not statistical, but a different sort of middle point. And so it's what the center of it is. Again, that central tendency. The mode is the most frequently scored item. And so if out of that 50-point exam, if the most frequently scored item was 48, that 10 people scored 48, hey, good on you, class, then that's the mode. That's the most frequently scored. Now, these are important because they help us to understand what the statistical average is inside of this whole sample size, and we'll talk about that in just a minute. And so we can measure whether or not our sample is representative of the population by some of these measures of central tendency. But in other cases, these measures of central tendency can be helpful, and you can prefer some of them over others. And so in one example is housing. So let's say you live in a neighborhood and you have, let's say the whole neighborhood has about 100 homes. And on average, the home price is $300,000. That's the statistical average. So if you add them all together, and they're $300,000, and so that's where it is now. Well, let's say that you want to, that someone, your neighbor, decides, you know what, I'm going to turn my home into an 8-story home, and I'm going to buy the 3 houses around me and create an 8-story crazy mansion that's worth $3 billion, right? And so it's this giant home. I'm totally joking. Maybe never be $3 million, whatever you want to call it. Giant home, suddenly super expensive, but all the other homes are still worth $300,000. So this is a moment where the statistical average, the mean, would be inflated by this one house that's super expensive, whereas the median, which would be the middle price, would stay roughly the same. It should stay exactly the same, actually. And so this is where we would prefer one over the other, because if the mean, let's say that the price of homes, because of that went up by, $300,000, it doubled, and so suddenly you look at the mean of what the home prices is, and it's $600,000, but the houses really aren't worth that much. It's just that one house that's pulling up the value. The same thing could be true in the opposite direction. That let's say you live in a neighborhood, this is actually more common, where you have a whole bunch of houses, 100 houses that are roughly worth $300,000, but then you have a few homes that are, say, foreclosures or something happened to them, and they're worth half that price. Well, that number, right, that price will actually drag down the rest of them. And so the median home price would be preferred over the mean. Well, some other ideas that we've also talked about, so it's a bit of a refresher, are types of sampling. And so we've talked about this before, where there's two types. There's non-probability and probability. So non-probability or non-random sampling is where we cannot use statistical power to generalize, because it's not a population that is considered to be representative, or I'm sorry, it's not a sample, that is considered to be representative of the population. And so these are the types of samples that are of convenience, they're purposive, they're quota, they're network sampling or snowball sampling. These are not ones that we're going to be talking about today. Instead, we're going to be talking about probability sampling. This is where we have random assignment across the board, where every person has an equal chance to participate inside the study. And the reason why that's important is because we believe that by using random assignment that we can look at the population as a whole, and if we random pull out all these different people, that they will help make up a sample that is actually representative. Now, we can do a systematic or a stratified. We talked about this before. Stratified, where we roll the dice, start on the third person and go every third person from there, or start on the fifth person and go every second person. Or systematic, where everyone just has an equal chance. It's just draw of a hat, that sort of thing. And so those sampling ideas are important because, again, we want that representative sample of the population. Again, sample size is that other idea that we need a balance between convenience, what can we actually do, and statistical power. Smaller samples lead to more types of error, meaning that the sample itself is not fully representative, whereas a larger sample has much more confidence. When we have confidence, it means we trust it more frequently. So, it gets back to, both the random sampling and larger sample size gets us to that metaphor, comparison to a chocolate chip cookie. I talked about this before. If you go over to Costco today and you walk by and they're giving samples of something, the whole point of giving a sample of something at Costco is that you get a taste of whatever it is. And so if they're giving samples of chocolate chip cookies and you're like, oh, I want a chocolate chip cookie because, Costco's awesome. And so you go over there and you take a little piece of it and you don't get any chocolate chips, you're kind of like, That's not a chocolate chip cookie. That is a sugar cookie. And they told me it was chocolate chip. Now they're lying to me. And so this is one of those moments where you want a representative sample, that you want chocolate chips in your sample of chocolate chip cookie, because that's, what a chocolate chip cookie is all about. And so the sample size, if they give you a tiny little crumb of that, it's less likely you're going to get chocolate in it. And the bigger piece they give you of the chocolate chip cookie, the more likely you are to actually have a sample that includes chocolate chips. Now, if they give you the entire cookie, then of course you get the entirety of it, and that would be the population. And so, if the population is made up of lots of different types of people and lots of different people across different regional areas and all kinds of stuff, then we need a large enough sample that would include all of the different types of people, just like the chocolate chip cookie. So then that gets to the question of how do we do that? We've talked about this before as well, so this is just review. How do we gain individuals into a study? That is actually a lot more difficult than it appears. If we send them by mail, some people will just discard that. If we try to call people on the phone, some people have landlines, some people have cell phones, some people are on the do not call list. If you meet people on the street, then what street do you choose? In front of the grocery store, which grocery stores? If you go online, a lot of people will treat that as spam. So how do you find the best sampling practice? And there really isn't a good answer for that. And different, statisticians and different social scientists will give you different answers depending on what they believe. There's no perfect way, and so you do the best you can. And like I talked about before, the response rate is actually really difficult. I gave you that example of the survey that I sent out to a whole bunch of people in the Western States Communication Association, and this is a survey sent out to people that really appreciate surveys, and I only got a response rate of 25%. And that's after me, pushing and prodding and really trying to get them. And so this is a moment that shows you that even people that are social scientists aren't responding to surveys. And so it's really difficult to get people to respond. Okay, so all of this is to say that if we have all of these processes that are going on in our sampling, that we can get finally to our hypothesis testing, because that's really what the magic of it all is. So if we have hypotheses, it relies on the assumption that a sample accurately reflects the composition of the population. So the sample itself must represent the whole. That chocolate chip cookie, that little bit's got to have chocolate chips. So the belief is that the distribution of some value within the population is normal and falls within particular limits. In other words, if I believe that a chocolate chip cookie is supposed to have chocolate chips in it, then I believe the sample should also have chocolate chips. If I believe that the chocolate chip cookie also has flour in it, then I would believe that the piece that I get would have flour or has sugar or whatever it is. In a population, if I believe that a population has attitudes about something or behaviors about something or skills about something or knowledge or feelings about something, then I believe that those are distributed normally, that everyone has the same chance, so to speak, to have those feelings. And so if I'm going to look at feelings about organized sports, then I'm going to look at the population, and everyone's got an opinion of some sort about organized sports. And so when I ask questions about it, that there's going to be a normal distribution inside the population. So my sample, if it's going to reflect that normal distribution, has to be large enough, it has to be achieved appropriately enough, it has to be randomly acquired, all those sorts of things. So the idea is that when we do our hypothesis testing, that we assume that the sample is representative of the whole. And it's a huge important step, because if it isn't, that we can't generalize. So it is possible to estimate the difference between the sample and the population. And so if you've ever, because you think about it, if it was perfect, if we could get a sampling procedure that was absolutely perfect, we'd do it every time. But just like I talked about, gaining a sample is difficult. So we know that there will be some level of difference and that we can account for that in the social sciences. And this is called sampling error. If you've ever looked at presidential polling or election polling or attitude polling, like the Pew Research Center, those sorts of folks that do attitude polling all the time, what is the state of the country? What do you think about this? What do you think about this person? What do you think about the president? What do you think about anything? They'll oftentimes have that bit that says plus or minus 3 percentage points. And that is a section that basically says that we've accounted for the fact that our sample is not 100% representative of the population, that it isn't large enough, or the means by which it was acquired are questionable. And that's a big question if you think about it. If you go to, in presidential polling, if you go to election polling, should you poll people who are likely voters or eligible to vote? Because that's a big question, and that affects the sample. Should you look at people who voted in the last election because they're most likely to vote, or people who just say that they vote sometimes? Or are you going to look at registered voters or non-registered voters? And so again, this is a very difficult type of sampling, but that's when you have those moments when people say plus or minus 3 percentage points. It's because it's a reflection upon the incompleteness of the sample. And so it happens in almost all types of polling and all social science research, but you can do this work with a level of confidence. And so that's what we're going to talk about is how we look at our samples and then some types of statistical measures that we can do with them. If things were perfect, we would have a normal curve. And you've probably heard of this as like a bell curve. And this image is taken out of your textbook. So within this bell curve, you can see, as you look at some of these things, the statistical, actually it's the mean, median, and mode is the very center there, that funny U thing. And so the U thing there is to talk about that is the center point of the data. That's the mean, median, and mode are perfectly aligned. The statistical average is in the center, the median is exactly in the center, and the mode is exactly in the center. That's how a perfect bell curve operates, along with the standard distributions that are going off. And so if you look at this, in a distribution that you believe to be normal, again, a normal distribution in your sample, you believe that each one of these sections, I'll draw on the screen here a little bit, that here is your normal, this is your mean, median, and mode, right? And so from there, you also believe that each one of these is a standard distribution. And each one of these contains some portion of the overall sample. So if on this side, in the middle, if that's the dead center, then this is 1/2 of your sample, and this is the other half of your sample. And it is believed that about 99% of the sample can be accounted for. It's like 99.7% can be accounted for within 3 standard distributions from the mean. And that means that each one of these, right here, this is 1, this is 2, this is 3, here's 1, 2, 3. These are standard distributions. So, again, let's go back to that idea about, let's say, organized sports. If everyone's kind of like, yeah, organized sports are okay, and most people think that they're okay, that might be our mean. They're right there in the center. But if there are people like, organized sports are really cool, I think that they're great, those people might be in this section. If there are some people that say, organized sports are the best, oh, I love them, and they're here. And then there are people that are like, I would die if it weren't for the NFL. Those people are here. Conversely, over here, you have the same sort of attitude. I might die because the NFL exists. I'm so over sports, I just can't handle it anymore. And so there are the various attitudes that are inside of the sample. So this is the normal perfect distribution. We have other types of distribution that, again, come from the problem of skew. And this is the problem of the distribution of values. And so if we have values that don't distribute appropriately, then we have to start to think about whether or not our sample is representative of the whole. Again, in normal distribution, the mean, median, and mode are the same. So here's another normal distribution. So in different types of skew, like in negative skew, you can see how there's a push toward the sort of the top half. And so on the left there in the histogram, you see that there's a negative skew toward the higher scores there. In a positive skew, everything's pulled toward the front. And so the same sort of thing. And so this is where the values are pushing one way or another. One of the easier ways to see this is on an exam. Now, I know you would love to think that in an exam, that if everyone gets an A, then heck, that's great because everyone got an A, and that means that everyone's super smart. But in the academic world, if we presume that there's a normal distribution of students, that means that there will always be A's, B's, C's, D's, and F's. And I'll tell you, I had a professor back in my undergraduate career that took all the scores and forced a bell curve because he believed in it so adamantly. So if everyone got A's, the A minuses would become F's. And so that's a crazy belief in how the bell curve operates. And so nobody liked him, by the way. And so if you look at the histogram on the left, the negative skew, again, if we look here, if everyone got A's, then that means that we have a negative skew, the A's and B's. Here's the A's and B's. And then if everyone failed the exam, then that means everyone got D's and F's. I'm enjoying writing on the screen, by the way. And so if this happens, then we can believe that there's something wrong with either our population, our sample, or the measure. And so it's probably the measure in some way. And so that's like the exam is not either reflecting what's supposed to be learned, it's too easy, it's too hard, or it really could be that the sample is just not representative of the population. Other types of skew that are more complicated, leptokurtosis is where you have a peaked curve. This is where you could actually have the mean, median, and mode are pretty close to each other, but there's a huge spike in the middle. So on an exam, everyone got C's, and there's only a couple A's and a couple F's and D's. Or that there's a very flat curve where there's an equal number of A's, B's, C's, D's, and F's. And so that's a platykurtic curve. And so these different types of skews, again, mean that the population, or the sample, is not representative of the population. It could also mean that there's something wrong with the exam in this example, but I think the assumption here we're working with is we're talking about our sampling techniques. So the last thing we're going to talk about is some inferential statistics, because most of the mean, median, and mode sorts of things, talking about averages, numbers of things, frequencies, those are really just, basic descriptive understandings. And I'm not going to get into depth about inferential statistics because there's all kinds of crazy stuff you can do. But really the magic of the discovery paradigm is not just being able to talk about what is, it's more about what is the relationship between things. Inferential statistics allows us to make those arguments and inferences and generalizations from data sets. And so again, we have those important assumptions: populations are normally distributed, and that the samples follow the population. So just bear with me on that. So as we think about inferential statistics, there's a couple different things that we can do. There are a couple of common statistical analyses that we can utilize. One of them is, or a couple of things we can do, is the testing across groups, or between groups rather. One of them is a t-test, and this is really common in the work that I've done. So a t-test is basically a comparison of mean scores between two groups. So if we take two groups of something, okay, let's take, in the example that we've been using frequently, it has to do with drinking habits. And so if we have high risk in one group and low risk in the other, and so here's our two groups, what we can do is take the mean scores about what those two groups are, and so we can compare them. So a good example we've done in the past is talk about, let's take the people who drink a lot, that report that they drink a lot, we're going to put them into one group. We put the different sorts of people in a different group, and we say these are the low risk drinkers. They don't drink hardly at all, or they drink within safe limits. And so across the high and low groups, we can say in the high group, let's compare, let's say GPA, or let's compare attitudes towards something, or let's compare something else. And so we can look at the number of the differences between those groups. Another way of doing it, if we didn't want to do high and low risk drinkers, something even more simple, let's take year in school. So let's take first year students, second year students, third year students, and fourth year students. And we ask the question, on average, how much do they drink, and how does that compare to other groups? Pretty simple. We can take the number of, do a t-test and look at the different types of scores on the number of drinks they had the last time they drank, or the number of, the frequency at which they drank, how many nights a week, something like that, that we can compare across groups. Now, t-tests are really helpful if you're doing a control and experiment sort of experimental design. And so if you have a control group and an experimental group and you want to compare between those, that's going to be really, really helpful. And this is something we did in some of the programs that I did where we did the alcohol testing. Remember I talked about that with experimental design, that we had a control group and an experimental group, where the control group took the survey beforehand, the experimental group took the survey afterhand. And we would compare across those groups. And the measure we used was called a t-test. And so that's how that works. An analysis of variance is looking at a comparison between multiple groups, specifically looking at how, when one thing goes up, how does another thing change? And so an ANOVA, an analysis of variance, is really used for understanding correlations. And so if we're trying to figure out not just who drinks more, but is it the case that if someone drinks more, if you have a whole sample, if drinking goes up, what happens to academic performance, say for example? Or what happens to, if drinking goes up, what happens to attitudes toward negative consequences of drinking? Do heavy drinkers recognize that there are consequences to their behavior more than light drinkers? How do they understand the harmfulness of alcohol? And so that's another common usage of ANOVA, and that's something that I've done in the past as well. So when it comes to correlations, we've talked about this before, there are, we're always looking at the relationship between two variables. Positive relationship, everything's going in the same direction. As one thing goes up, the other goes up as well. Excuse me. Negative relationship, when one thing goes up, the other goes down. A no relationship, which is the zero one, where there's nothing, a flat line. And a curvilinear relationship. The curvilinear one is probably the hardest to understand. I'll keep it in drinking terms here because I think it's one way of understanding it. There's a law of diminishing returns when it comes to drinking. And this is a great way of understanding how the curvilinear relationship goes. And so if students know this pretty well, those who drink, that if we take a night of drinking and we do this sort of curvilinear thing, as we start the night of drinking, we have some drinks and just have a couple of drinks. And as you know, things are looking great, and they're going well. And then all of a sudden, you have a few too many, and then all of the negative side effects start to come in. That's the curvilinear relationship. It is not the case that when it comes to drinking that you could have, just keep drinking, and that the relationship would always be positive. That, if we're thinking of the variables here, it's the number of drinks and fun, right? It's not that you can just continue to drink for the entire night, because at some point in time, the negative effects of alcohol will kick in. And so, it's a funny way to see it, but experienced drinkers know that they need to get to that point and then not continue to drink and just stop. But a lot of folks don't realize that, especially a lot of younger folks that first get to college campuses, and they experience those negative effects quite severely. And that's where you have really bad things like alcohol poisoning or other sorts of sexual violence and things like that, where people don't understand that curvilinear relationship, the law of diminishing returns when it comes to alcohol usage. Now, correlations can be interpreted in lots of different ways. And if there's no relationship, it's a flat. There's no relationship between all of the ideas. If there's and I'll explain some of this in a little bit. 0.01 to 0.25 is a weak relationship, and then so forth. 0.625 to 0.55, a moderate relationship. Strong relationship up to 0.75. A very strong relationship in 0.99, and a perfect relationship would be 1.00. Now, we're going to play a game called Guess the Correlation here a little bit, but we'll come back to that because that'll be important for you. But if we want to understand how we think of our data, we can think of it through scatter plots. So let's say that we're going to continue this example with alcohol, and that x, the x-axis, which is the bottom one, is a variable that measures the level of drinking. So this is a study that we're running on trying to understand what happens when drinking, what are the consequences of drinking on a college campus. Because I'll tell you what, folks always want to know that. What happens when your students drink? This is a big topic of conversation within health and wellness and in health communication and on college campuses, because there's, student deaths, there's retention issues, all kinds of things. Lower academic performance, it's a big problem. And so y is going to be the level or the variable that measures levels of academic attrition, which means dropping out. And so the presumption here is that the more students drink, the more likely they are to drop out. That's the correlation that we're testing. Now, if there were a perfect relationship here, the line would look like this, just like we talked about. And what that means is that every point of data would exist right on that line. And that would be a perfect relationship. So each little dot that I'm making here is one data point. So this one right here is one student. We'll name that student Bob. Bob is right there in the middle. That's my terrible handwriting there. And that's one survey, one item, and that measures one bit of data. But if we take all of them, all the Bobs and all the people, and we keep looking at the data here, and if there was a perfect relationship, it would line up exactly on this line. But you know what? It usually doesn't. And so we take away this perfect line, and instead what happens is that we test this relationship where you have the data looks more like this. It's all over the place. That line shouldn't be there, my bad. And so the data is like this, and you start to wonder, wow, what is going on here? And what is this? This is just everywhere. Well, what we can do is try to take a couple of lines and see where does the vast majority of the data fall. And the statistics will end up looking at the relationship between here and here. Now, the presumption is that the vast majority of the data, that within usually this 3 standard deviations from the mean, somewhere around there, that's the ideal. Is you have let's say 99% of our data exists within these limits. Okay. Now, the distance from here to here is how we can understand the correlation and the strength of it. And so, if that distance, the smaller it gets, then the more perfect it is. And so this is how we can understand how data operates within a correlation. Again, if it were really tight, all the data is really right in this line right here, that's going to be again, we can draw our lines here and look at the space here. And there you have a very strong correlation where, as you can see, as the drinking levels go up right here, that means that this high drinker over here is most likely to drop out or did drop out. And so that's the levels of attrition. So we might look at this across all college campuses. The campuses that drink the most, do they have the highest levels of dropping out? Then they'd be way up there. Campuses that drink the least would have the lowest levels of dropping out and would be way down there. And that's what we're going to look for. So that's how correlations work. So now I'm going to get you to play a game here. And the game is called Guess the Correlation, and I'm going to want you to go to this website called guessthecorrelation.com and earn a little bit of extra credit. So the extra credit you're going to earn here is going to be about how well you can guess the correlation. And I'll show you how it works. So if you go to guessthecorrelation.com, you'll see this screen, and what I want you to do is do a new game. You have to enter in a username. I'm going to name the name of my cat, which is Barley. And now Barley's good. Oh, Barley already exists. That's not fun. Well, I have 3 cats, so we'll do Hops. And you get an idea there about Barley and Hops. That already exists too. We're going to do Spurgetyberg, and there's that. Bunch of random stuff. There I am. Okay, so whatever you want to put in, it doesn't matter. So now we're going to do a new game, and now you try to guess what is the correlation on this screen. And so if you try to figure out how wide is that, how do I understand it, I'm going to guess this is a pretty low-level correlation. So I'm going to put in 0.2. Oh, well, look at that. Perfect. Perfect. I just got a bonus of 5 coins. And so now I can continue on my streak and guess again. Okay, that's looking a little better. I'm going to go 0.5. Okay, I'm close enough. Okay, I'm on a streak here. Oh, that's looking, that's 4 maybe? Oh, I am very good at this game, aren't I? Let's go 5. So you can see how this works. So what I want you to do is to get as high a score as you can. Eventually you'll lose. Ooh, that's a good one. We'll go 0.9 on that one. And so you see the true R is the level of correlation there. That's about a 7. See, I guessed wrong. And when you guess wrong, that's what happens. And so if you guess wrong enough times, you lose. I'm going to go with 1. Oh, that's actually right. 7. Okay. So at the very end, you're going to get a score. Now, send me your score, send a screenshot of this, and so you should be able to figure out how to take a screenshot with your computer and send your high score to me, and I will afford you extra credit points. Now, it's not going to be the number of points as per the score, so if you did this and you got 18, I'm not going to give you 18 extra credit points, but I promise I will make it worth your while if you got some high scores, and highest score in the class will get an extra special bonus. And so go ahead and send that to me, and we'll have some fun with that. So, those are some basic foundations for understanding statistics. Let me know if you have any questions. Remember, the whole point of this is to get a sense as to how these mathematics, how these numbers can be quantified and understood to try to make sense out of the types of survey data and things that we're collecting. As always, let me know if you have any questions.